Hello and welcome to another day of Advent of Code. This is day 3 and the difficulty on day 3 ramped up quite a bit. So let's jump into it. Okay, so the problem for day 3 is getting some signals and multiplying them together. I don't know. I didn't really read much of the prose. I kind of just jumped to the actual constraints of the problem. But anyway, we're going to see input that looks similar to this, a bunch of ones and zeros. Each line represents a binary number. And for part 1, we are going to try and figure out two different numbers. We're actually trying to figure out two different numbers for both parts, and the way we find those two numbers is different for each part. But in part 1, we are going to try and count the bits at each position. So at the first position, you can see there's some number of ones, and there's some number of ones here, etc., etc. And to find each of the two numbers, the first number is going to be the most common bits in each position. So I think there's more ones than zeros in the first position, so we'll see a 1 at that position in the first number. I don't actually know. I'm not going to bother counting them. But the first number is the most common bits, and the second number is the least common bits. And then at the end, we're going to multiply those two together. I found part 1 much easier than part 2. We'll get to part 2 in a bit, but let's start with this. So since we're going to be looking at each of these lines, I found it best to loop over each line. For line in input as dot split lines. And the core part of this problem here is counting the bits at each position. And for that, I kept track of the bits. There's kept track of the counts. There's kind of two ways to do this. The way I did this in my solution is by making a multiplied zero list. So counts equals 0 times the length of, actually it's probably easier to do. Just keep track of the lines before, lines 0. This is one way to do this. Basically gets you a variable that's the length of this and just contains a bunch of zeros. That's one way to do this. The other way that I've just thought of is to use our friend default dict. And I have a video on both this technique as well as default dict that I will link in the description. I actually kind of like the default dict solution a little bit better. We're switching it up. We're doing this live. But basically, we're going to use this to keep track of, and this is going to be a map from int to int. And yeah, at each position, we're going to have a count of the bits. Okay, cool. Next, we need to iterate over the strings, or the characters inside of these strings. And for that, we're going to do for I comma c in enumerate line, we're basically getting the index, and that'll be in I, and the character, which will be in C. And if C is equal to 1, that means we found a 1 bit in this position. We're just going to increment the counts in here. Counts I plus equals 1. And actually, you know, whether this code actually looks the same, whether or not I did it as counts equals 0 times len line 0. It's kind of a neat little bit of Python where the same syntax can work for two different data structures. Okay, cool. So once we've computed the counts, then we need to actually build up these two numbers. And for that, I did a little bit of bit twiddling logic. I'm going to do this without bit twiddling and then show you how I can switch it into being slightly more clever. And so let's, we're going to build up number, I think they were called gamma and delta or something in the actual numbers, but we're just going to call them num1 and num2. And we're going to make them lists of strings, and we're going to build up, we're just going to put little zeros and ones into them as we go through these. Okay, so we need to loop over every position in this. And for that, I'm again going to do a loop that's, you know, maybe not the best. Usually you don't want to do range len loops, but and maybe we make a better constant for this. Maybe we make like line 0 length, and then it's less hacky. But we're gonna loop over each position, and we know the counts of the bits because we have them here. and we know kind of the halfway point to decide whether they're more common or less common based on the length of the number of lines divided by 2. So we can say if counts I is greater than the length of lines over 2, then we know that the bit was more common, and or the 1 was more common, and so then we can do num1 dot append 1 and num2 dot append 0. Otherwise, we know it was less common, so we'll do 0 and num2 dot append 1. And so after this, we've built up a series of 0s and 1s. Let's actually print kind of our intermediate here to show you what we've got. Num1, num2, and yeah, so you can see we have 1 0 1 1 0 and 0 1 0 0 1. And you'll notice kind of a neat thing here. We actually really only need to compute one of these numbers because this one is the binary inversion of that number. So you could actually completely short circuit or shortcut looking up number num2 and just use some binary magic to get there. The trick, well, I'll show you. Well, I can just show you the trick right now. So if we have binary 1 0 1 1 0, which is this number here, and if we just do this so that we can see that it's still in binary, and if we XOR that with -1, -1 is a series of all entirely 1 bits. Right, it's going to print it as negative. Maybe that's not so helpful in Python. Anyway, you could invert all of these by doing that or by doing an inversion. The problem is Python's representation is just going to tell us the the negative here, which is less useful than I thought. Okay, never mind. We're not going to do it that way then. Okay, but anyway, once we've done these, we need to convert them back into integers. And the neat way to do that with Python is you can use int with base 2, and that'll parse your integer for you. And so that's, and you can, if you want to convert it back into binary, you can do bin again, just as I just showed. So that's kind of how you can convert these. And so we print our answer. Part 1 will be int, and we need to join the number list string things that we made in base 2 times int of num2 in base 2. And probably in reality, I would put this expression on its own line, but we're just kind of hacking this together because it's advent of code. Python 3 t.py. Cool, and we get the expected value for part 1. Now I want to talk a little bit about, yeah, let's improve this to do this entirely in binary instead of having to deal with these strings here. And we're going to use a little bit shifting trick here. So we're going to start with both of these numbers being 0. And basically what we're doing is we're deciding a bit, and then we're going to move it over. Deciding a bit, and then moving it over. And since we're going in order from the most common bit, at the end it should be exactly the number that we want. And so what we're going to start by doing is left shifting each of these numbers by 1. So this left shift operator, you have a number, and if you shift it by 1, that's what this double arrow operator is. You can see the bits moved over by 1. So we basically just added a 0. You can also think of a left shift as a multiply by 2. Since it does exactly the same operation, and some compilers and CPUs will optimize either of these multiplications as one or the other, whichever one's more efficient at the hardware level. But yeah, anyway, we're going to do a left shift of 1, which shifts our bits over. And now we really are just deciding whether we add a 1 to the end of the number. So we can just do num1 plus equals 1. We don't even need to do anything with num2 here because it implicitly has a 0. And in the other case, we add 1 to num2. And so that'll get us basically the same computation, but we stay entirely in integer land instead of mucking around with strings. And this is how I approach the problem. Okay, so that's part 1. Oh, I guess we'll talk about algorithmic efficiency first. So this operation here is going to be linear over the number of lines, and this is going to be linear over the length of the line. So you can think of it like as ONM, but in this case, m is pretty small, and so you can kind of think of m as a constant factor, so it's kind of linear. It's a little bit tricky to talk about the algorithmic efficiency for this part here. But then we know down here, this is just a linear scan. This is OM, where m is the length of the line, and we're not really doing any non-constant lookups here. And so this is all a constant factor. And so overall, it's ON times m, or ON if you consider m to be a constant factor. Okay, part 2 is where the difficulty really ramps up, in my opinion. You basically need a way to somewhat efficiently represent these numbers, and I came up with a couple of different ways to think about this. And unfortunately, the code for this is kind of long, so I'm going to show you kind of my thoughts in Paint, and then and then I'll show you kind of ways I solve this, as well as some other ideas on how to make this more efficient. I guess before we go on to part 2, there are a couple of potential optimizations here that I didn't bother with. One thing that you can do here is, instead of iterating by rows, you could iterate by columns, and you can stop as soon as you've exceeded a particular count of ones or zeros. So you at most only need to parse about half of these lines rather than parsing all of them. And yeah, I didn't do that here. Like it doesn't actually improve the overall runtime efficiency. Like, it would still be linear, but it's about half of the amount of work that you would have to do. And so that's one way to optimize at least this part here. I don't think there's much to go to benefit here, though. Okay, but yeah, part 2. So the first way that I thought about this, and I spent a really long time actually writing this solution, so it was kind of tricky. There is a data structure in programming called a trie. And what a trie is basically a specialized tree that stores some amount of data at each node. And so we can kind of represent our strings of binaries here as, well, the root node's not super interesting. But the basic structure that I had here was some count, which was an integer, and then a left, which was a nullable node, and then the right, which is actually I called this 1 and I called this 0 in code, which was a nullable node. And I'll show you the actual code for this in a sec. Oops, there's a typo there. And basically, I stored at each node the number of things that were there. So if we inserted, the root node's gonna have all of them. So you can imagine this has, I don't know how many there were. Say there were 15. And then you basically have a branch that goes to one of the either ones or zeros. And you have another node here. This represents however many things you have there. So let's say that 6 of them went here and 9 of them went here. And so then you know which is the most common bit to go down. So if you're looking for the most common bit, you would see that 0 has a count of 9, and you would traverse in this direction. And basically, you would traverse down this tree until you find your single value. Like, say this was, well, we can't quite reduce them that quickly, but say that we eventually got to some amount of depth down, and then we have one that has a count of 1, and that means that we have found our value. And the cool thing about this structure is any lookup in here is logarithmic. You're only looking at the individual bit paths that you need to take. You don't actually have to traverse the entire data set at once. And so my first solution built up this data structure and then traversed it. Let me show you that. My code's actually a little bit gross for this, because I was drinking before stream and did not have time to improve it much. But yeah, so here is kind of my solution for that. And yes, the code is very long. This is the part where I'm building up that data structure. And note here that I didn't have very good data types here. I mostly was just stuffing things into dictionaries. I was trying to go fast. I wasn't really trying to make this nice looking. And so unfortunately, I have some kind of unsightly stuff here. But basically what I did is I looped over each of the lines. We started with a root node, and for each line, we have kind of a current node. And as we traverse through the characters, we increment each of the counts. and we set up a new value for that character. So this is kind of assigning the 0 or the 1 to have its own new node, and then we recurse down there. So we start by looking at this node, and is it a 0? Okay, cool. We go to this node, we create it if it doesn't exist, and we increment the count here. And then now that we're looking at this node, we look either left or right to get 0s or 1s. And so that's kind of how I built up this structure. As for traversing it, I'm basically starting at the root node, and we decide whether we go left or right based on the count of the two values. Note that I kind of have like a little bit of an ugly hack here where I have to continually retrieve either an empty dictionary or the value and check whether its count is. I really don't like this. This usually this definitely indicates a smell in my code that I have kind of false data. I have a data structuring problem here. Usually get is kind of a bad smell in programming, but anyway, hacking it together, trying to get it to work, that's really what I was aiming for here. And so basically what I'm doing here is I'm keeping track of the path that I am taking down this route, and I'm doing that logarithmic lookup here. I'm assigning current to whatever the next bit is in this. And if I ever reach a point where the count of the values is exactly 1, then I know I have found my particular number that I'm looking for, and I break out of this loop and I keep track of my prefix. Because it is possible that I've narrowed it down to 1. Is it possible? I think it's possible that I've narrowed it down to 1 before there. Oh wait, no, because there's... Huh. Yeah, maybe that's not necessary. Anyway, yeah, I could probably get rid of this prefix thing now that I think about it, because there's always going to be enough numbers there. But yeah, this is how I find the most common number, or at least the prefix of the most common number. And then I do basically the same thing for the least common number. You'll notice all of this code is duplicated except for this operator changes to this operator. I saw some clever solutions where this was put into a function and this value was just inverted based on whether they were looking for most common or least common. That is one way that I could reduce half the lines of code here, which I think is a good refactor. But I basically do the same thing, except instead of looking for the most common, I look for the least common. At the end, this is again kind of a little bit of a hack. Since I only recorded prefixes here, prefixes, I don't know. I then have to go back and scan again for the number, the particular line that I'm looking for, and then I multiply them together. So this did work for me. It's a little bit clunky. There's a lot of code here, but it kind of worked out. I guess if we talk about algorithmic efficiency, this is actually the same operation as the first problem, except I'm building a different data structure, and creating dictionaries and assigning them is amortized constant time. So you can think about this as, again, O n times m, where n is the number of lines and m is the width of the line. As for my lookups here, these are actually a bit faster. These are going to be logarithmic. I guess they're technically O of m if you consider m the length of things, because we have to potentially do that many lookups. We do those twice, so it doesn't really add to it. And at the end, I do another linear scan here. This doesn't affect the runtime, but it does potentially make things slower. So overall, this is O of n, or O of n times m if you want to consider m the length of strings. Okay, so that's my kind of tree approach here. I took another approach. I wasn't satisfied with that answer, so I tried a different way. I think this one is a little bit simpler, and there's actually another simplification that I found in some other people's solution. Instead of actually building that structure, I basically just pivot the entire set of lines. That's what this does here. So instead of looking at it row-based, I turn it so it's column-based. And then I can directly query whether something is more common or not, which is basically what I'm doing here. And so the way I actually did this is I kept track of which lines are alive. So we can do another paint drawing here. So let's do 0, 1, 1, 1, 0, 0, 1, 1, something like this, just to make it easy for me to compute. So when I started, all of these lines are considered live. Where's our brush? And so you can imagine, let's actually do the circle. I'll look a little bit better. You can imagine that I started with a set of all of these. It actually doesn't need to be a set now that I think about it. I think it can just be a list. And so for the first bit, say we're looking for the most common bit. We're going to keep all of these alive because they all have a 0. And then we look at the next column. The most common bit is a 0, so we eliminate this. We've only kept these 3 alive. Then we go to these 3. Again, 0 is the most common, so we eliminate this one. And then we come down to these ones, and this is the tricky part of the problem. The tricky part of the problem for me is handling the edge case where you have an equal number. In the equal number case, for the most common, you pick 1, and for the least common, you pick 0, which actually makes it a little bit convenient because it mirrors itself if you invert the problem. So in this case, we would eliminate this, and now that we have found exactly one item, we can return that one directly. And so I represented that by having a set of all these. I actually don't think it needs to be a set. I think this can be a list because I don't actually use it as a set. Yeah, I just loop over it. So there's no reason for this to be a set. I might change it to a list. But basically, while I have at least one candidate, I'm looping. I find the particular column that I'm looking for. I actually don't need this path at all. That could be an integer. Yeah, that's what you get when you program in the middle of the night and don't really think about it. But yeah, I build up the same path, and again, like I didn't really need it because I can just look at the current character instead of doing this. But basically, I whittle down the included thing based on whether we have the most common or the least common. And again, I have the same copy paste here, but I could have just changed this operator and inverted that, similar to what I talked about before. And this actually has essentially the same algorithmic complexity as before. This is an O n times m because we're looping over each line and looping over each character. This is O of m if you consider m the length of the line, even though this is... actually, this is slightly slower. This is O n times m because this is looping over each character in the input, and so this is going to be slightly slower. In reality, this solution was actually faster because it didn't do as much data manipulation. So depending on the data size and data structures, it may have been different. But yeah, after that, basically, find the best and worst lines. Since we've already narrowed it down to exactly one index, I can use next iter to pull the one thing out of that list and then multiply them at the end. And yeah, this code isn't the greatest. I would clean this up if I had more time. One cool thing that I saw that made this problem easier, and I kind of alluded to it in the way I drew this here, is if you sort your input, finding which things are included or not is just a binary, kind of a binary search. You just find the middle number and eliminate the top or eliminate the bottom. So you can potentially get this solution down to about, I guess it would be log n at that point. Well, you have to do a sort, so it'd still be n log n. So actually, I think that would still be slower. But it's a cool way to think about the problem rather than having to keep track of these live or unlive things, or by building a structure like this. But anyway, that's day 3. a lot more complicated than the previous days. Hopefully you found this useful, and I'll see you around for the next set of Advent of Code. See ya!